In this video, we're going to start looking at ways that we can calculate the delta H for a reaction without actually needing to do the reaction first, using pre-existing data that has been collected in a few different ways. So we're going to talk about one way today, which is known as Hess's law. And really, Hess's law is sort of at the heart of all of the different ways that we're going to talk about this. So we often want to know some idea of what the enthalpy change of our reaction is going to be before we do it. The best example of this is that if a reaction is extremely exothermic, if it releases a lot of energy, that is something that's good to know in advance for safety reasons, that you want to be aware that energy is going to be released by this reaction and you need to account for that in order to perform the reaction safely. Also, exothermic and endothermic reactions are favored under different conditions. So knowing that can help you make the reaction run efficiently and give you the maximum yield possible. So with Hess's law, the first method we're going to talk about for doing this, essentially what Hess's law tells us is that regardless of the steps that a reaction takes, the delta H for the overall reaction is just equal to the sum of the delta H's for the individual steps. So if we don't know the delta H for a particular reaction, but we know delta H values for some other reactions that we could use as steps, note that the reaction doesn't actually have to go through those steps. But if we can write it on paper like it does, we can add up the delta H values for those steps, for those other reactions, since we know those, to get the delta H for the reaction that we're interested in. So with this, if we can express our reaction as a series of steps for which we do know the delta H, then we can figure out delta H for the overall reaction. The one thing that we need to keep in mind is that the equations for our steps must add up to the overall reaction. In order to add up their delta H's. And this makes a lot more sense when you see it in action. So let's say that we want to find the delta H, the enthalpy change for the conversion of graphite into diamond. So we're looking for the delta H for the conversion of carbon in its graphite form to carbon in its diamond form. If we don't know that, but we know the delta H for the reaction where graphite reacts with oxygen to form carbon dioxide, if we have that delta H, as well as carbon dioxide reacting to form diamond and oxygen, we have that delta H, that's all we actually need. So essentially what we're looking for is reaction 1 plus reaction 2 needs to equal the overall reaction in order for delta H1 plus delta H2 to equal the overall delta H. So we're looking to essentially, pretty much like you would do in math class, add these two equations together, cancel out anything that appears on both sides, and we should be left with this. If we're not, it doesn't work. We'll talk more about that in a moment. So what we're looking for here, I usually think about splitting it down the middle, that I want to add up everything on the left side, I want to add up everything on the right side. So I am looking to have graphite somewhere on the left. My overall reaction has graphite on the left, which means one of my other reactions has to have graphite on the left. And I find that in reaction 1. I also need to find diamond on the right. My overall reaction has diamond on the right. So one of my other reactions needs to have diamond on the right-hand side. And we find that in reaction 2. So everything we need is present, that when we add all of this together, we have the graphite. When we add all of this together, we have the diamond, and they're on the proper sides of the reactions. But you'll also notice I've got this extra stuff. But if we look closely, we find that we have an oxygen on the left and an oxygen on the right. So when we add these two equations together, we have oxygen on both sides. It's not actually doing anything. We can subtract oxygen from both sides or cancel those two things out. So the oxygen up here is going to cancel the oxygen down here. And similarly, for the carbon dioxide, we have carbon dioxide on the left in reaction 2, on the right in reaction 1. Those are going to cancel each other out as well. So once everything else is canceled out, the only things we're left with are the things that are actually a part of our overall reaction. That means that these two reactions add up properly. Reaction 1 plus reaction 2 does equal the overall reaction. The only thing that didn't cancel on the left was graphite. The only thing that didn't cancel on the right was diamond, which is exactly what we see here. So that means that our overall delta H is just going to be delta H1 plus delta H2, which gets us a total of positive 1.9 kilojoules per mole. You don't have to include the plus sign when it's positive. You do have to include a negative sign when it's negative, but you will often see a positive sign included just for clarity to say that, yes, this is definitely positive. I will usually include it in most of our thermodynamic stuff. So in kind of summary here, what we did was add up everything on the left. And add up everything on the right. And then cancel anything that appears on both sides. So the next thing we need to talk about is what happens if they don't add up correctly. We can't use our reactions as they are until they add up in this way, until everything that's not part of our overall reaction cancels out and everything is where it's supposed to be. So if things don't quite add up properly, we're not out of luck, we just need to do a little bit more work. So if our reactions don't add up, we can do some rearranging in order to make it work. So the one thing we need to keep in mind is that rearranging affects our delta H as well. So if we need to rearrange our reactions, we just need to adjust our delta H's accordingly, but it's really predictable. So there are essentially two different ways that we can alter a reaction in this type of problem, in a Hess's law type of approach. The first thing we can do is reverse a reaction. So if something is on the wrong side, if it's on the left side in one of my steps, but I need it on the right side in my overall reaction, I can flip the reaction. I can reverse it. Products become reactants, reactants become products. When I do that, I'm converting between the same materials, but I'm going in the opposite direction. So the same amount of heat will transfer in the opposite direction. Means all I need to do is change the sign of delta H. So for instance, if I know that 2 moles of hydrogen gas reacting with 1 mole of oxygen to form 2 moles of water vapor has a delta H of negative 1144 kilojoules per mole, then the reverse reaction of that would be 2 moles of water reacting to form 2 moles of hydrogen and 1 mole of oxygen. So you can see my product became my reactant, my reactants became my products. So the new delta H for this revised reaction is positive 1144 kilojoules per mole. Same amount of heat is transferred, just in the opposite direction. The other way that we can rearrange our reactions is to adjust the coefficients. So we can multiply or divide our coefficients by some factor. And we do have to adjust our delta H as well. When we're changing the coefficients, we're changing the amount of moles of substance that we are representing as reacting. If we're reacting more material, there's going to be more heat transferred. If twice as much stuff reacts, twice as much heat is transferred. If half as much stuff reacts, half as much heat is transferred. So all we need to do is multiply or divide delta H by the same factor. One thing to note here also is that you must multiply all coefficients or the reaction will no longer be balanced. And you do always need to be working with a balanced equation. So if you are doubling the coefficient of one of your reactants, you have to double every single coefficient in the reaction, reactants and products. And we would do this if we had the wrong number of molecules. So if we needed 2H2O and we only had one, we could double it, or whatever the case may be. And we'll see an example of that in a moment. So here we have some examples. We have that same reaction forming water with negative 1144 as the delta H for the reaction that we know. So if we look at how these first two reactions compare, going from the one we know the delta H to the next one, we've doubled all of our coefficients. So 2 became 4, 1 became 2, 2 became 4. So we've taken everything in this reaction and we've multiplied it by 2, which means that we need to do the same thing to our delta H. Twice as much heat is going to transfer when twice as much material reacts. So this will be negative 2288 kilojoules per mole is the enthalpy change for this reaction. And then for the third one, going from the one we know down to this guy, we've cut all of our coefficients in half. So you can think of it as either dividing by 2 or multiplying by a half. Doesn't make a difference. Personally, I always think in multiplication. And that means we need to apply the same change to our delta H. So we're multiplying that by 1/2. So the delta H for this process is negative 572. So we can also apply both of these transformations to the same reaction if we need to. So we have two options. We can either reverse a reaction or change its coefficients, but we can also combine those however we need to. So we can do both at the same time or do both to the same reaction. So for instance, between these two reactions, we have reversed the direction. So we have, instead of taking hydrogen and oxygen to form water, as we are in the original, in the second one here, water is reacting to form hydrogen and oxygen. And we have also cut all of our coefficients in half. So we just need to apply those same transformations to our delta H, that we're going to change the sign and multiply by 1/2. So this will be positive 572 kilojoules per mole. So now let's look at an example where we need to do some rearranging in order to solve this problem using Hess's law. So we have these two reactions that we know the delta H for, and this reaction down here is the one that we're trying to solve for. So we're going to need to rearrange some stuff. Looking at our final reaction, so we can think about what's on the left, what's on the right, where do I need things, how much do I need? Right now, I have 2 NO2 on the left. So I need to find somewhere in one of these reactions 2 NO2 on the left. If it's not there, I need to make it. I can reverse a reaction if it's on the wrong side. I can multiply by the coefficient, multiply the coefficients if I don't have the right number, if I don't have 2. And then I also need 1 N2O4 on the right-hand side. So take a minute now and try and do that. See if you can rearrange reactions 1 and 2 to put these things where they need to be. So what you should have found is that we have 1 NO2 on the left here. So we have our substance on the right side, but we don't have the right number. So what we need to do here is multiply this whole reaction by 2. So we'll have 2 NO2 forms 1 N2 and 2 O2. And since we doubled the amount of material that's reacting, we will also need to double the delta H. So we're also going to need to multiply this by 2. So that's going to be negative 67.8 kilojoules per mole. So this original version of the reaction is not going to be helpful to us anymore. The revised version gives us the 2 NO2 that we need, and this revised delta H is the one that we're going to use when we're adding things up at the end. Then, trying to find where is my N2O4 here. It is currently on the left-hand side, which is not where I want it. So what I can do there is reverse my reaction. So if I reverse my reaction, reactants become products, products become reactants. And I just need to change the sign on my delta H. So this will become positive 9.8 kilojoules per mole. Original version of the reaction, not helpful. The revised version puts N2O4 where I need it. So the revised delta H is the one that I'm going to use. At this point, we should find that everything else cancels out. And if we look, we have 1 N2 on the left in reaction 2, 1 N2 on the right in reaction 1. Those cancel out. We have 2O2 on the left in reaction 2, 2O2 on the right in reaction 1. Those cancel out. So everything is where it needs to be in the correct number. We don't have anything extra, which means that as we have them now, reaction 1 plus reaction 2 equals our overall reaction, which means that our revised delta H for reaction 1 plus our revised delta H for reaction 2 gives us our overall delta H for this process, which comes out to -58 kilojoules per mole.